Trying to develop our knowledge and understanding is perhaps one of the most human things there is. We are constantly attempting to broaden our horizons and make new discoveries. So today, here at Unexplained Mysteries, we will take a look at 3 recent scientific breakthroughs. Particle physics could be rewritten after shock W boson measurement. Sometimes theories go unchallenged for decades, standing the test of time, withstanding any new information and revelations that are thrown its way. And sometimes, despite unwavering loyalty to a theory for decades, with evidence and calculations standing in support, all it takes is one new discovery to throw everything slightly off course. In the world of particle physics, a new measurement of the W boson could have done just that. One re-evaluation that has changed our understanding, possibly forever. The standard model of particle physics is the current lens through which we view the world. Our entire understanding of how the different elements and aspects of the universe interact with one another is grounded in and stems from the standard model of particle physics. Despite us standing by the standard model, we know it is flawed. So the possibility for a finding to revolutionize our understanding is truly thrilling. This measurement of the W boson has the potential to entirely alter what we thought we knew. Measuring the W boson has been a piece of research in the making for years, a decade even, and this new result will be met with incredible levels of scrutiny, checking for accuracy, reliability, and how rigorous the research has been. Martin Mulders, working at the CERN Particle Physics Laboratory near Geneva in Switzerland, wrote a commentary piece on the W boson measurement which will be published in the academic journal Science. Mulders said, "It would be the biggest discovery since the start of the Standard Model 60 years ago." So what exactly is the Standard Model of particle physics? The Standard Model focuses on 3 forces, with bosons mediating each force between particles of matter. The 3 forces are electromagnetism, the strong force, and the weak force. The weak force is what causes radioactive decay, and it utilizes the W boson as a messenger. The W boson was first detected back in 1983. Its central role to the theory has left scientists on a quest to gain an accurate, precise insight into the mass of the boson practically since its discovery. Until now, all of the measurements that have been taken largely aligned with one another, and so this was considered to be evidence that the standard model might hold some validity. Despite the standard model being the working assumption, we do already know it is wrong, or at the very least, far from complete. For example, in the standard model, we do not take into account an explanation for how gravity works, how dark matter works, or why we do not have antimatter in our universe. This has meant scientists are on a keen lookout for anomalies, for strange results, or peculiar findings that could spark a whole new strand of ideas, theories, and hypotheses. Ashutosh Kotwal at Duke University in North Carolina and his team were the ones to gather this far more precise data. Their research used data gathered from the Tevatron Collider in Illinois. Their team found what to us non-scientists may seem like a small amount, though it has the potential to have a huge impact upon the field. The new data placed the W boson's mass at 80.4335 gigaelectron volts, with the previously accepted mass being 80.379 gigaelectron volts. Kotwal and his team of course understand how outlandish this claim sounds, with it having the potential to turn the entire discipline of physics onto its head. Kotwal claims he and his colleagues have exhausted the possibilities to test this idea from their end. Now, other professionals will replicate this experiment, spend hours poring over data, statistics and equations to see if this is a genuine and credible finding. Kotwal stated, "We think the answer is holding up to our own scrutiny." This research does have the potential to be groundbreaking, but that is if it truly holds up. It's important to question why this result has diverged so far from what our expectations of it were. We need to take the steps to understand why before we attempt to create a new model. What makes this process so difficult is the transient nature of particles, with W bosons quickly decaying into other particles, often electrons and electron neutrinos, or muons and muon neutrinos. Neutrinos are incredibly elusive and notoriously difficult to detect, so tracking the W boson is a much harder job than it sounds. If the other researchers do not find any complications with the work of Cotwall and his team, then the next stage is to begin producing another measurement. This means more work at the Large Hadron Collider, and the only collider we have in the world with high enough energy to form W bosons at all. We have a lot of work left to do before re-theorizing, though the potential and significance of this research is truly monumental. Physicists may have found a way to create traversable wormholes. The rules of the universe are fairly fixed, and the aim of some of the greatest areas of science is to try and understand what these rules are. Fun favourite sci-fi tropes often like to toy with these rules and play with the ideas of what if they were not there. It's this kind of rule breaking that leads to ideas like getting lost in wormholes and the fun space-themed dangers we see on the big screen. In reality, the idea of wormholes could exist in the rules laid out by the general theory of relativity and the standard model of physics, but these were not traversable, meaning you cannot move through them. That is, until now. A wormhole is a theoretical structure. The idea is to think of it like a tunnel, where the two ends represent different points in space-time. This means that you go into the wormhole and emerge in the same place at a different point in time, or at the same point in time at a different place, or at a different point in time and in a different place. People are still speculating whether wormholes could possibly exist. Sure, they do not go against the ideas of the general theory of relativity, but we certainly have never seen any. In 2021, a team of physicists working at Princeton found a loophole in this wormhole theory. With the ideas laid out through quantum mechanics in a 5-dimensional universe, it could be possible, according to these researchers, to create a wormhole large enough for a human spacecraft to travel through and could spit out the astronauts on the other side of the universe. However, this idea is purely confined to the mathematical and theoretical world. It is highly unlikely for something like this to naturally exist, and our modern technology is nowhere near advanced enough to facilitate something this complex. The idea that wormholes may exist and that they could be travelled through is truly so fascinating, though it does not seem like we will be skipping around the universe anytime soon. Gliese 1214b. Gliese 1214b, or GJ1214b, is an exoplanet that orbits the star Gliese 1214, around 48 light-years away from our Sun. This planet is truly fascinating, with it having the nickname the Waterworld, due to it being the most likely planet that we know of to be an ocean planet. An ocean planet is a terrestrial planet with lots of water on its surface, for example, Earth. It's even categorized as a super-Earth in size, as it is a little larger than Earth, but significantly smaller than the gas giants. The Waterworld exoplanet was first detected by the M-Earth project, searching for the way that brightness of a star dims when an orbiting planet passes in front of it, as viewed from Earth. This was discovered in 2009, when a drop in the brightness of the GJ1214 star was seen. There is not a lot that we definitively know about this exoplanet, though we can make educated guesses and suggestions based off information we have gathered from planets that we can observe. These ideas and suggestions outline GJ1214b, or the Waterworld, as having a thick gaseous envelope, taking up 5% of the mass of the planet. It has also been theorized that this planet is rocky, or like a mini Neptune, or an ocean planet. If it is indeed an ocean planet, then the overall understanding is that we can expect it to look like a hotter, bigger version of Jupiter's moon, Europa. There is so much that we still do not know about this exoplanet, though the exploration into worlds so far from our own is truly thrilling. From understanding the rules of the universe to seeing what else lies in it, it's truly an incredible world that we live in. But what do you make of these recent physics discoveries? Be sure to let us know your thoughts in the comments section below and help us by growing this community while working to solve these unexplained mysteries. Thank you for watching, and don't forget to subscribe for more videos.